Uh, Hi Nidir. So I'm recording this video for work energy power. We'll talk about work energy power. So we'll just do a basic introduction and maybe a couple of questions, and then whatever doubts you have, we can attend it on Tuesday onwards. Okay. Okay. So work energy power, because you've done the question before, I'll make it a little quick, and I won't make it very heavy. So let's try to like just keep moving. Okay. Okay. So of course, work energy power is about work, energy, and power. So these are the three things we'll be dealing with one by one, right? It's so work is a technical term. Again, I'll be using my Jamboard and everything. The setup remains the same. I've opened your book, and I think it should be okay. I know that this might be tough, but just rewind and then just see it like that. Okay, anyways, let's get started. So work, it can be many things, right? So you say that you work, your dad works, I work, right? Like, but in physics term, work again, same with power also. Like you can have political power, you can have other types of power, but then in physics terms, these are all technical terms. So meaning that they can be measured. So the way that work is defined, it is defined very simply as, where is my Jamboard? Let me pop this out. Okay. Maybe I should add another screen here. Let me add that. Hmm. Or we can just keep this and I can keep hopping in the middle for these things, right? Otherwise, what we can do is this, and maybe I just keep hopping between two, uh, this thing. So hopefully you can still see what's going on. So that way things are good. Yeah, this is good. Okay, so we're going to talk about work, energy, and power. The first topic at hand today is work. Okay, so let's get started. So, work, as I said, is a technical term which is defined by W equal to force into displacement into cos of theta. So, this is the only three formulas we'll be talking about today. This is the first formula. So it's force into distance into cos theta. So let's just try to visualize it a little bit. So you have a block and you're applying say a force on it, and then it moves the distance d, right? If you push a block, then it'll move a distance d, right? Uh, in this case, the work done will be equal to force, which is the magnitude of the force that you're applying, into d. Maybe it moved say like 10 meters and you applied say 100 newtons of force. So your and then cos of 0 here, 0 degrees here, which is the angle. So this is the angle between the force and displacement, right? So this is the displacement, not the distance. Then you have a force here, and then this is the angle between that. You must know. So in this case, the angle between this is the force, this is the, so if you draw the force vector and if you draw the displacement vector, then they are on top of each other, which means that the angle between them is 0 degrees. So cos of 0 we know is 1. This just becomes force into displacement, right? Here force for us is 100 newtons times displacement is 10 newtons. So simply work done is, so units will be 1000 Newton meter, which we can say is just equal to 1000 joules, right? So this is what we want to keep in mind, that the unit of force is what we call joules, right? All this is very basic. Okay, so the second thing that we want to talk about on slide on Jamboard number 2 is that whatever work you do, Okay, this is not the second formula that we will be discussing, but so whatever work that you do will be equal to the change of kinetic energy, right? So what does that mean? So say you take a block and you push on it, right? Because you push on it and it moves a certain distance, uh, that means you have done that much work. But what happens towards the end is this guy, when you stop applying the force, is now moving with speed, right? Like you can imagine that now it is moving with some speed, even when you leave it. So kinetic energy, which is simply given as half mv square, right? We know this, so in the next we'll also derive this a little bit, but at least for now, let's take it as this. So kinetic energy, uh, so at this point, kinetic energy is zero, but at this point, kinetic energy equal to half into mv square. At this point, the reason why it's zero is because v is zero here, right? And then v becomes something. So at this point, kinetic energy increases, right? So we see that so there was a force that was applied at this point. Okay, that force did some work on the object. Sorry about that. On the object, and then the body has increased kinetic energy, right? So it is very straightforward. You do some work, you increase its kinetic energy, anything at all. Let's take another example. It's very straightforward. You'd have a ball, and that ball starts to fall, right? When you leave it, maybe you're holding the ball and then you remove it. So the ball starts to move, starts to fall down, right? So in this case, what do you think? Who is doing? So because its kinetic energy is increasing, right? Because kinetic energy is increasing, we must say that work was also done somewhere on this ball. Now let's ask who is doing the work here. So when we draw the free body diagram of the body, meaning that we analyze what all forces are working on it, because we have stopped holding it, we are not applying any force. The only thing that's applying a force is the force of gravity that's falling down, right? So which we might guess that the gravity is doing the work. So in this sense, we'll discuss everything a little bit more, but just a basic idea is gravity is doing work here, okay, which is increasing kinetic energy for this body. Right? This is what we see. Okay. So let's keep going. So the next thing that we want to talk about is work can be positive or work can be negative. Okay. Uh, so what that means is sometimes you try to push a body and it starts to move, right? As we discussed. In this case, because if we again come back to the formula for FD cos theta, so we see that it can be positive when cos theta is positive and negative when cos theta is negative, right? So let's first discuss when is cos theta positive. So cos theta, if you remember, is positive in the first quadrant and in the last quadrant, right? So that means the angle between the force and the displacement must be in this quadrant. So let's try to see it. So if the body is moving in this direction, D, then the force must be somewhere in this area. Meaning that if the force is acting like this, then the work is positive. If the force is acting a little upward, then also the force is positive. If it's acting downward, then also it's positive. So in a similar way, if you have force acting like this backwards and then D is acting forwards, D means the body is moving forward but the force is trying to push it back. That means there must be, maybe there are a couple of forces and each force individually is doing work. So maybe one is trying to push it up and then another one is trying to push it to the right. So this force, so in our example here, maybe there is a force F1 that works like this, maybe there's a pushing force that works here. So as a result, maybe the body is moving in this direction for some reason. So then this is the direction of D, but the work done by this force F1 is negative. So if we say it like this, that work done by F1 is negative. Why? Because this angle, which is same as this angle, is greater than 90 degrees. So it falls in the quadrant where cos theta is negative. So work is negative. Is that clear? Okay. And what about say, sorry, so I called both of them F1s. Let's call this one F2. So this work done by F2 force, in this case D is in the same direction as F2. So cos theta is, this is the first case that we talked about. So D and F are in the same direction. So cos theta is 0. So theta is 0. So cos theta is 1. So work done in this case is positive, which is equal to F into D. Right? So that's one thing that we need to understand. Now, if we understand positive and negative work properly, uh, so let's try to answer this question, right? So there is a ball that's trying to go up. Okay, so maybe we have thrown it up and then we have left it, of course. The moment that we leave, the ball exits out of our hand, we are applying no force. But then we still said that the gravity is still there, right? Which is as a force working on the ball. In this case, what do you think the work is, positive or negative? So what is the work done by the force of gravity on the ball? So to check whether it's positive or negative, we just need to check the direction of D, which is upwards, and the direction of force, which is downwards. So in this case, it will be negative. Why? Because D is like this, and then F is opposite of that. Right? The angle between them is always 180 degrees. Okay. Uh, what if when so the ball goes up, right? But then it starts to fall down. In that case, the ball when it comes down, then the D is in downward direction, and the force of gravity is still pulling it down. At that point, work done is positive. So first work done was negative when it was going up, and then it was positive while going down. Now why it is positive here is because theta becomes equal to 0. Right? So here theta was 180 degrees and then theta became 0. Right? Okay, so this, if we understand this, then if it can be positive or negative, then on the next Jamboard, let's discuss if it can be 0. Can work be also equal to 0? Okay. So to understand whether it can be 0 or not, let's just look at the formula again. FD cos theta, right? So we can say that, okay, maybe work is 0 when force is 0, or maybe D is 0, or maybe cos theta is 0, right? Maybe one of these three is 0, then force can be 0. If cos theta is 0, we had seen, right, that in this area that the work done is positive. In this area, work done is negative, right? What about on this line, on the y-axis line here, right here? Maybe work is 0, and which we know is true because cos of 90 degrees, when theta equal to 90 degrees or 270 degrees, then the work is also 0. So let's consider examples of each of them, right? So the first one, when force is 0, let's look into that. So if force is 0, then there is really no force. So a body is just at stationary, or it can just be it can just be sliding. If there is no friction here, then it can be just sliding with constant velocity, right? In both of these cases, there is no force acting on it. There was a force acting perhaps on the second body at some point in the past, but at this very point, there is no force acting on it. So there is no work done. So in both of these cases, work done is 0. Right? No force, no work. Consider this example now for case number 2 now, that there is a wall and then maybe you're trying to push a wall, right? So how much ever force you put on the wall will never move. Okay, in this case, D is equal to 0, so work done is 0, even though you might be pushing the whole day, right? Like similar case with say you went somewhere and then you came back, right? In this case, D is not the distance, D is the displacement. So because D is 0, again work is 0, right? Now for the last case, which is cos theta equal to 0, we said theta must be 90 degrees or 270 degrees, right? So the angle between the force and the displacement must be 90 degrees. So when does this happen? So this is a tricky scenario. So say something is already moving, right, with the velocity v, and then you try to maybe push it to in a perpendicular direction. What do you think will happen? Maybe it will start to move up, right? When it starts to move a little bit up, you again, the direction of velocity will become a little bit upper, right? Now the force is still perpendicular to the velocity. So when it reached here at this point, then the direction of velocity was upwards and it was trying to move there, right? Even at this point, the force is 90 degrees, so force must be applied like this. So the force has kept up with the velocity and it has also changed the direction, right? So first force was acting directly up and the body was moving upward. The body wants to now move a little bit upward. Now so the force also now changes direction. The body moving like this, it starts to push this and then it moves like this. Now even at this point the same thing happens, right? So maybe there is all the new speed here is again more inclined towards upward direction and it starts to move like this. Again the force needs to change direction and become like this. Maybe the step after this, it needs to again change direction and the force becomes like this. Do we notice something? Maybe it is forming a circle, right? That's what our intuition is telling us. So in a circular case, when there is circular motion, the circle is not very good, but in a circular motion, the direction of velocity and the direction of force are perpendicular. So in this very case, we say even though the force is turning the body, there is no work done by this force on the body, which we can also see by the fact that the velocity of the body remains same. It is always v, right? Okay. So this is a very quick introduction about work that we have discussed. So now let's get into energy a little bit. Okay, let's keep moving. Okay, so we are going to now discuss about energy. Okay, now energy is nothing but it can be different things. So okay, 1 second. Okay, let's first define something called mechanical energy. Okay, mechanical energy is nothing but kinetic energy plus potential energy, right? Do we know both of those things are? Yeah, roughly we know, right? So say uh, a ball is kept here at the ground and then it starts moving and then maybe it reaches at a height and then it falls down, right? To some level. So at this point, somewhere in the middle, it is moving with some velocity and it must, and then at the bottom also it's moving with some velocity. and at the top maybe it stops for a bit, so velocity becomes 0, and then velocity changes direction, and then it becomes with the same velocity v1 but downwards, right? It changes direction. This is the just the path of a ball, right? We have studied this in previous chapters. In this case, the kinetic energy is simply half mv square, right? And potential energy is equal to mgh, right? Okay, so one thing that we need to understand is, so mechanical energy can be, we can find at different points, right? So at say point, the lowermost point, let's call it A. If we try to find potential energy at A, then potential energy may be at B, that which is that I'm saying that is the topmost point, even though it's not showing. Maybe let's just consider that this is the topmost point, and then at point C. So let's try to find kinetic energy, potential, so potential energy here, what we are measuring is gravitational potential energy, of course. So it's potential energy, and finally the mechanical energy, right? So kinetic energy at point A is nothing but half into m into v square, which is v1 square here in our case, and then potential energy is mg into h. H from here is just 0, right? This h is 0. Okay, so this is just equal to 0, so mechanical energy is half m v1 square, right? At point B, our half m v1 square where v is 0, right? So the kinetic energy at B is 0, right? And but potential energy, we have something as mgh. Whatever height it rises to is mg capital H, right? So mgh, right? And the at C it is minus v1 square, okay, because it is moving downwards. But then v1 square minus gets cancelled. It is same as half m v1 square, but potential energy is 0, and then we have similar to half m v1 square. Okay, so we see that this energy and this energy is same. Okay, so let's try to look at this middle energy and also try to prove something about that. So do we need to know what h is now? Okay, so that we can find by simply the kinematic equation that we had learned in the previous physics chapters. So we know that we will use the equation, kinematic equation, S equal to ut plus half a t square, right? And we'll look at this scenario. Okay, let's not use this equation. Let's use v square equal to u square plus 2as, right? So in this case, a is equal to minus g here because it is acting downwards, right? And u here is equal to v1, right? And final v is equal to 0 because v is the final velocity. So final velocity is at point B, initial velocity is at point A, which is plus v1, and then finally this is so now we can plug in these numbers and we can just simply get 0 equal 0 square minus v1 square plus 2 times minus g times, here s is the distance traveled. In our case that will be just h, right? Okay, now let's simplify this further. 0 square is just 0, and then this is v square, so it's minus v square, right? Minus 2, I'm taking this minus out, minus 2gh. So just to be clear, this is not a plus, this is a minus, right? So simplifying this further, v square is v1 square by 2g. Okay, now we have a formula for h. Now let's try to put this formula in for h, right? And so after putting it in, we get mg times h. H is v1 square by 2g G gets cancelled and we get voila mv1 square, right? So this mv1 square is also equal to now all three. So we see that whatever energy we have is always conserved. Conserved means always, so this is a term that we use. Conserved means that it is always equal. It's never lost. Right? So whatever energy we had at A is the same energy we had at B, is the same energy we had at C, and any energy that we had even at a point D or a E in somewhere in the middle. Okay, so just to be clear, so kinetic energy at A we have as something. Okay, it falls down with time. It falls down with time, falls down to B where it becomes zero, and then it rises again to B. This is the kinetic energy, right? And similar to this, potential energy is minimum at A, then it goes to B, which is the highest, and then it falls down to C. But as a result, if you add these two, then mechanical energy is always constant at any point, right? This is potential energy, and then we have kinetic energy here, right? So just take some time. This might be too much. Just rewind the video a couple of times, but you will get it. Just work through things slowly. We'll discuss if you have any doubts. Okay. The last thing that I want to discuss is power, which is on the next slide. So power is simply defined as a work by time. Okay. Its units are watts, uh, megawatts. You might have heard these terms somewhere, or maybe calories. Uh, no, so calories is a unit of energy, is a unit of work or energy, which is the same thing. Okay, so watts, megawatts, horsepower is also. So I'll just tell you the conversion. This is 10 to the power of 6 watts. Watts is represented by W. Horsepower is 746 watts. And these are the commonly used units, right? So you must have heard ki, okay, my phone has a 15-watt charger. Okay, if you have a laptop that maybe has a 65-watt charger. Okay, you may have a you may have an AC that consumes 1500 watts. Okay, an average light bulb, LED light bulb around also consumes around 15 watts. Like this is for phone charger and a light bulb. So these are the rough things, right? So the formula for power is basically work by time. So if you have work done in any amount of time, then you can find power, right? Another way to also find work is also force times velocity. Now I would leave that as an exercise for you, but I'll ask you next time to derive force times velocity from work by time. Try to derive the second formula from the first if you can get it. Right? If you have this, then uh, so let's do one example for power, maybe. Okay, so maybe uh, you have one of the examples that people discuss is what is the power consumption of human body, right? So let's try to work it out. It's not. So we know that a human body consumes 2000 roughly calories, what we call kilocalories in a day, right? So this is the conversion that we know. So this is what we know. Okay, we need to find what is the power consumption. So power consumption will be the work done or the energy or the work done by time, right? So whatever work or energy, so energy we know is this much, so it is 2000 kilocalories by time. Now time is 1 day, but you don't want to write 1 day here, right? So the units of power must also always be, so this should be expressed in seconds, not a day. And then this should be expressed in in joules. So let's try to find those conversions, right? So 1 calorie equal to is 4.2 joules, right? And 1 day is 24 hours, and then 60 minutes in an hour, and then 60 seconds in total. Okay, now with these two conversions known, can you tell me the power consumption of human body? Okay, so this I'll leave as an exercise for you, but we'll discuss next time. So this is a very basic introduction. We'll definitely do more sums and more things around it, but that we'll likely to do together. But this is like a very rough basic introduction for things. Just go through this and let me know if you have more doubts, right?